Hello, class. Welcome. This will be the lecture on chapter 5. Let me set everything up so you could see my screen. Let's see. All right. So you should be able to see my screen now. All right. So once again, this chapter is on, this lecture is on chapter 5, which is on z-scores, the location of scores and standardized distributions. And for this particular chapter, some of the learning outcomes that I want you to get once this lecture is over is a deeper understanding of the z-score as a location point in a distribution of scores. I want you to understand how to transform a raw score or an X or what is called an X value into a z-score, and also how to do it in reverse. So change the z-score back into an X value or a raw score. I want you to be able to describe the effects of standardizing the distribution and how to transform scores into a standardized distribution and how to transform the standardized distribution back into raw scores. So some tools that you'll need to be good in this particular chapter, right, is going to be understanding the mean. All right. So in all the future chapters that we work on, the mean, as you know, as a measure of central tendency, is one of the more important, if not the most important measure of central tendency that we'll be working with, because it sets the foundation for all the formulas that we'll be using to run our statistics. Also, as a complementary part of the mean, the standard deviation. That's it, the second most important thing, because standard deviation, for things I talked about last lecture, will tell us a lot about the distribution of scores and where an individual score lies in comparison to the mean and to other scores in the distribution itself. And then there's this basic algebra, all right, which I told you in chapter 1. Please review the appendix to get a brief, to briefly refresh yourself on the basic algebra that you would have come across in, junior high school or early high school. All right, let's continue. So the introduction and the purpose of a z-score, right? So what is a z-score? What does it do? Why is this important to understand? Well, a z-score is going to help us to identify and describe the location of every single score in our distribution of scores. All right. So it's also going to help us to be able to what is called standardize an entire distribution. All right. So standardization is something we're going to talk about a little bit later in this chapter, but essentially it helps us to be able to compare scores from different assessments or people's scores in different distributions and make comparisons on them. All right. A lot of times standardization is going to make everything a lot easier to understand what's going on with the data. And we'll talk more about that. We'll also, z-scores also help take different distributions and, again, like I said earlier, make them equivalent and comparable. So a good example of this is, let's take baseball, for example, right? How could you compare the performance of a player in 1968 to a player in 2021, right? Some things that we know that scoring was much lower in 68. So if we simply looked at their raw batting averages, right, or home runs hit, the player from 1968 would likely appear to be much worse. But if we were to standardize their scores by comparing them to the mean batting average or home runs hit in 1968 or in 2021, well, we now have a common metric to compare the scores by how well they did relative to other players in that particular season. Another kind of example, the standardization of IQ scores, for example. So, although there are several different tests for measuring IQ, the tests usually are standardized so that they have a mean of 100 and a standard deviation of 15. And so, because all the different tests are standardized, all right, it is possible to understand and compare IQ scores even though they come from different tests. For example, we all understand that an IQ of 145 is extremely high, where an IQ test, no matter which IQ test that we use. So in general terms, the process of standardizing takes different distributions and makes them equivalent. And once they're equivalent, we can then compare them. All right, let's continue. So let's say there are two different people, and they are taking an exam, right? In two different classes, right? And so in the first distribution, the mean, right, which we learned last chapter, the mean is 70, and the standard deviation is 3. The score that this person received on that particular test was a 76, right? Which is 2 standard deviations above the mean, right? So they have a fairly high score, right? Fairly high score, because anything that's 2 standard deviations or more or higher or lower than the mean is we would consider to be, again, an extreme score, right? But let's now look at the same mean, right? Same mean, but now our standard deviation is much larger. The standard deviation is 12. This person, let's say this is the same person who took a test in different classes. Well, now their score is 76, right? And a score of 76, right, is less than 1 standard deviation above the mean, because 1 standard deviation above the mean would be 82, right? This is half a standard deviation above the mean. So if we were, trying to figure out, right, who's kind of doing better, well, we would say, hey, this person right here is doing better because their high score, is more standard deviations above the mean than this particular distribution. All right. And so what we're going to do in this class, in this lecture, is talk more about how to compare these distributions so we can more firmly state conclusions about these 2 different distributions. All right. And so thus the relative location of your score within the distribution, right, depends on the standard deviation as well as the mean. Those are 2 important concepts. So z-scores and the location in a distribution, all right? So the exact location of a score is going to be described by a z-score. The sign tells whether the score is located above or below the mean. If it has a positive sign, it is above the mean. If it has a negative sign, then that means the score is below the mean. All right, that's very important to understand. the positive and negative sign of the z-score. It's telling you where this score is relative to the mean. The number, right, the number for the z-score tells the distance between the score and the mean in standard deviation units. All right. It's telling us how far away in distance something is in units of standard deviation. So let's look at what's called a standardized distribution using z-scores. All right. So in a z-score distribution, the mean is always going to be 0. The mean is always 0. And we are going to go up by 1 unit and below by units of standard deviation. So this +1 means this is 1 standard deviation above the mean. +2 means you are 2 standard deviations above the mean. If we went further out and we had a +3, that means that you are 3 standard deviations above the mean. And we're doing the same in the opposite direction here. So this -1, the negative means we are going to be below the mean. The score of 1, right, means that we are 1 standard deviation below the mean. -2 means we are 2 standard deviations below the mean. And if we went further out into -3 or to -4, well, those would be 3 and 4 standard deviations below the mean. All right. So for example, in the previous example, right, with the 2 distributions, I showed a distribution with a mean of 70 and a standard deviation of 3. In the distribution, a score of 76 would be transformed into a z-score of 2, right? The z value indicated that the score is above the mean by a distance equal to 2 standard deviations, or in this case, 6 points. But for the distribution, the mean of 70 and the standard deviation of 12, a score of 76 would be transformed into a z-score of positive, 0.5, or essentially a half a standard deviation above the mean. All right. So let's look at that, again, right? So if we were to use this z-score or the standardized distribution, right, for these numbers, right, this would be 0, because remember, in a standardized distribution using z-scores, the mean is always 0. So is this one. Mean is 0, right? We're going up by standard deviation. So if the standard deviation for the regular distribution is 3, well, a score of 73 would be positive 1. And then the person scored 76. Well, 76 is 2 standard deviations above the mean, right? So that's what that score is. So the score of the raw score of 76 is equivalent to a z-score of positive 2. Now, if we look at this one, right, this has, if we're using the standardized distribution, 0 is going to be the mean, and we're going up or down in units of standard deviation by 1. So in this one, in the distribution, the standard deviation is 12, right? So 70 plus 12 gives us 82. So this would be a score of 82 would be 1 standard deviation above the mean. So it'll be a positive 1. But right here, our score in this distribution is 76, which is halfway between 82 and 70. right? So this would have a z-score that would be equivalent to positive 0.5, or in other words, half of a standard deviation above the mean, half above the mean. All right. All right, so let's do some questions, kind of going over that, right? So the first question, and these are kind of questions that you'll see on quizzes and in your homework. And so it says, the first question says, identify the z-score value corresponding to each of the following locations in a distribution. Well, the first one says below the mean by 2 standard deviations. Now a z-score, right? They're asking you for the z-score. A z-score is in units, is in standard deviation units. So it says it's below the mean. So if it's below the mean, it's going to have a negative sign. So it's going to be, wow, that's not really good negative sign. It's going to have a negative sign, right? And it says it's 2 standard deviations below the mean. So our z-score is -2. This one says it is above the mean by half a standard deviation. Well, when it says above the mean, we are talking about a positive z-score. And it's above the mean by half a standard deviation. So it's a positive 0.5. All right. Next one says it's below the mean by 1.5 standard deviation units. Well, if it's below the mean, we know it's going to be negative. And and the z-score is in standard deviation units. So this is negative 1.5. So the z-score is negative 1.5. And so that is how you would answer those particular questions for a z-score, for identifying a z-score corresponding to different locations in the distribution. For number 2, it says describe the location in the distribution for each of the following scores. For example, a z-score of +1 is located above the mean by 1 standard deviation. Right? So this is a negative, right? So we know this is below the mean, and it's below the mean by 1.5 standard deviation units. So that's the z-score of -1.5. Well, this, even if they don't have it here, this is a positive, right? So this z-score is above the mean by 1/4 of a standard deviation. This right here has a negative, right? So we know it's below the mean. So this is below the mean by 2.5 standard deviations. And this one right here, remember, you got to remember this is a positive in front of this, even if they don't put it there. Well, this one is saying that it is above the mean, because it's positive, above the mean by half a standard deviation. All right. By half a standard deviation. And so going to question 3, for a population with a mean of 30 and a standard deviation of 8, find the z-score for each of the following scores. All right, so I'm going to do this what I consider to be the more difficult way, and then I'm going to go over a formula that we can all use in order to make this calculation much easier. So the information that I have is that there's a mean of 30 and a standard deviation of 8. So let's draw that out. So what I like to do is to draw a distribution, and I like to put where the mean is. So the mean equals 30, and the standard deviation equals 8. Now my score is 32. My raw score is 32. It's asking me what would be the z-score for a raw score of 32. Well, one standard, well, I know this is going to be a positive z-score because the mean is 30 and our score is 32, which is above the mean. So our z-score is somewhere over here, right? So it's a positive z-score. We already know that. But what is the z-score for this? Well, the standard deviation is 8. So if we wanted to know what one standard deviation above the mean would be, it would be 30 plus 8. So 38, right? So to get from 30 to 38, if you have is 8 points, right? Well, 32, you have to do some of this calculation in your head, is a quarter of the way, right? It's a quarter of the way to 38. It's a fourth of the way. 32, 34, 36, 38, right? So this would be a z-score. So z equals positive 0.2. I guess you can't write it that far over there. 0.25. All right. All right. So let's do a different problem. So in this case, the raw score equals 26. Well, 26 is lower than our mean of 30. So this is all, we already know this is going to be a negative z-score. Right. So the z-score, all right, is somewhere over here. Right. Well, the score is x equals 26, right? So x equals 26, right? And if we wanted to know what the score would be one standard deviation below the mean, it'd be 30 minus 8. So 30 minus 8 would give us 22. So we know that this z-score, this raw score is between 0, the mean, and 1 standard deviation above the mean, right? And so it is halfway between the two, right? 30 minus 4 gives us 26. Another 4 gives us 22, right? So this z-score would be z equals negative 0.5. It is half a standard deviation below the mean. All right, half standard deviation below the mean. All right, so let's clear that up. All right, so we're going to hop into question 4. For a population with a mean of 50 and a standard deviation of 12, find the x value corresponding to each of the following scores. Right. So this one we're doing it kind of backwards. So let's draw out our distribution. Right. This I made it much bigger this time. So now our mean equals 50 and our standard deviation equals 12. All right. The first one goes, hey, what is a quarter of a standard deviation below the mean? Right. Well, if our mean is 50 and and we're going up or down by standard deviations of 12, 50 minus 12 is going to give us what? 50 minus 12 is what, 38? So a score of 38 is equivalent to 1 standard deviation below the mean. All right. But they want to know what is a quarter of a standard deviation below the mean. Well, what you can do, and this is a calculation you're doing mostly in your head, but if the standard deviation is 12 and we're looking for a quarter, right? A fourth of 12 is 3. So 12 divided by 4 is 3. 50 minus that 3, so 50 minus 3 is going to give us 47. So our X score that corresponds to the Z score of negative 0.25 is 47. All right, let's say we're going the opposite way. Let's say, well, I'm telling you that the Z score is 2, all right? So where would this X value be, right? Well, we know that this is above the mean by 2 standard deviations, right? So one standard deviation is 12, right? So 50 plus 12 would give us 62. If we add another 12, that's going to give us 2 standard deviations above the mean. So 62 plus 12 gives us 74, right? So a Z-score of positive 2 is equivalent to a raw score of 74 if the population mean is 50 and the standard deviation is 12. All right. So that is a more complicated than we need it to be, right? A lot of stuff you had to do in your head. There's a simpler way to go about doing this, and that is by using a formula. All right, here's the answers for those questions. Here is the formula. This is the Z-score formula. So Z is going to equal the raw score minus the population mean divided by the standard deviation. So if you look closely, the numerator is a deviation score, right? We're trying to see how far away, how far that particular raw score is from the mean. It's a deviation score. And the denominator expresses deviation in units of standard deviation. So again, the Z-score identify a specific location of a score in terms of deviations from the mean and relative to the standard deviation. All right. So let's look at some work with that particular formula, the Z-score formula. So let's say a distribution of scores has a mean of 100 and a standard deviation of 10. What Z-score corresponds to a score of X equals 130? Right, so here's our bits of information. We know the mean, the standard deviation, and we know the raw score. So we just plug it into our formula, right? 130, which is the raw score, minus 100, which is the standard deviation, divided by, the raw score 130 minus the population mean of 100, divided by the standard deviation of 10. It's going to give us 30 over 10, which gives us 3 when simplified. So the Z-score is positive 3. All right, positive 3. We know the Z-score is supposed to be positive because the mean is 100 and the score we're looking for is above the mean, right, by 30 points. But that's a simple one. We could have done that one in our heads, right? The formula makes it easy because we can do ones that are more complicated. So let's say you had a mean of 86 and a standard deviation of 7. And our raw score is 95. And they're asking you to find the Z-score. Well, this one you can't really do in your head. You need a calculator, right? So you just plug these numbers into the formula. The raw score is 95. The population mean is 86. And we're going to divide that by the standard deviation, which is 7. If we simplify, we get 9 over 7, which gives us a z-score, a positive z-score of 1.29. So the score of 95 is 1.29, is above the mean by 1.29 standard deviation units. All right. All right. So that's how you use the formula, right? So determining a raw score from a z-score, right? So let's say if they give you the z-score and they want you to tell us what the raw score was, well, you are going to use this equation. And this is just an algebraic revising of this formula. All right. Instead of solving for z, we're going to be solving for x. And then you get this formula. So this formula is saying the raw score equals the population mean plus the z-score times the standard deviation. All right. So the raw score is simply the population mean plus or minus if the z is below the mean, and then z is multiplied by the standard deviation, and it gives you this particular formula. All right. So let's see some problems with this. Well, yeah, a worked out problem. So let's say we have a distribution with a mean, a population mean of 60, right? And a standard deviation of 5. So there's a lot of typos in the textbook. So if this is for a population, right? So if this is the standard deviation, it should be this symbol right here, right? But instead they have it for a sample, right? So just understand that the textbook, right, has some typos on it. But it doesn't take us out of being able to do the problem. So the population mean is 60 and the standard deviation is 5. And that corresponds to a z-score of -3, right? So this kind of goes in a weird way of trying to help you solve this. It's breaking it down, but an easy way to do this would be just plugging everything into the formula. So x equals, right? The formula is the population mean plus the z-score times the standard deviation, right? So x equals 60 plus -3 times the standard deviation, which is 5. So -3 times 5 gives you 15. 60 minus 15 gives you 45. All right, so make sure when you're using your calculator, you're putting in this information correctly, because sometimes people get tripped up by this part right there. All right, that's 45. So the original raw score is 45. Let me clear that up. Okay. So up till now, we were computing z-scores for populations, but we could also do it for samples. And usually samples is all we have. So we're normally using samples anyway. So if we are using a sample, the formula changes, right? So it becomes the z-score equals the raw score minus the mean, right? That italicized m over the sample standard deviation. So the raw score minus the sample mean over the sample standard deviation. And if we were trying to determine the raw score from a z-score, well, we just algebraically solve for x, right? And so we get this formula. X equals the sample mean plus the z-score times the sample standard deviation. All right, so those would be the formulas if we're dealing with a sample. Let's see. Okay, so let's go through some questions. So a score of a z-score of +1 indicates a position in a distribution, right? That is going to be above the mean by a distance equal to 1 standard deviation. So let's do another question. This one's a true or false. True or false? A negative z-score always indicates a location that is below the mean. Well, that is true, right? If the z-score is negative, that means it is going to be below the mean. It's the next question. A score close to the mean has a z-score close to 1. Well, that's going to be false, right? A z-score that is close to 1 means that the z-score is close to a standard deviation of 1. If the closer the score is to 0, means that score is closer to the mean. It's kind of a tricky question, right? But again, in the z-score, or what's called a standardized distribution, the mean is always 0. The closer you are to 0 in the standardized distribution, the closer the score is to the mean. All right. All right, so let's do this question. For a population with a mean of 50 and a standard deviation of 10, what is the X value corresponding to a Z-score of 0.4, right? Let's see here. I think I have this one. Give me 1 second, y'all. So I have a worksheet that I have put together. All right. So this worksheet is taking you, this is the chapter 5 worksheet. Well, let me make sure. I just want to confirm that you can see this. Stop the share. All right, let's make sure of this. Okay, so you should be able to see this now, right? So it's going to go through all the kind of problems that you need to be able to solve in this particular chapter. All right, so the question that we're working on now is asking you to transform a z-score into a population raw score, right? And so the information that they give us, right, is the z-score is 0.4. The mean, is it the mean? Yeah, it's population mean. So the population mean equals 50, and the standard deviation equals 10, right? And so you just plug it in to this equation right here. So X is going to equal the population mean, which is 50, right? Plus the z-score of 0.4 times, right, times the standard deviation of 10. So 0.4 times 10 plus 50 is going to give us 54, right? 0.4 times 10 is 4. 50 plus the 4 is 54. right? So this would equal 54. All right. Let's see, current slide. So the answer would be 54, just plugging it in to the X-score formula. Okay, so let's move on. So using a Z-score to standardize a distribution. So again, every X value in your distribution can be transformed into a Z-score, right? And so the characteristics of a Z-score transformation is that it's going to have the same shape as the original distribution. That's important. The shape hasn't changed, right? The shape hasn't changed. The mean, as you already know, the mean of the Z-score distribution is always 0, right? It's always 0. And the standard deviation is always 1. And again, like I've been saying, a Z-score distribution is called a standardized distribution. So let's look at that transformation. I kind of did already in some of the problems, but it'll be helpful to look at this. So let's say the population mean is 100 and the standard deviation is 10 in this population of scores, right? If we transform every single score to a Z-score, we're going to get the same exact distribution, except the mean now is going to be 0 and the standard deviation units are 1. So that's the only difference. And so this is just telling us that, hey, um, right here, this was one standard deviation, right? And if we transform this into a standardized distribution using Z-scores, well, it's the same distance, right? So everything's the same, except now the numbers have changed from 100 to 110 to 0 to positive 1. All right. And just a relabeling using Z-scores. All right. So using the Z-scores for making comparisons, right? So all Z-scores are comparable to each other, right? And scores from different distributions can be converted into Z-scores. So the Z-scores themselves, right, what are also called standardized scores, right, allow the direct comparison of scores from two different distributions because they have both been converted to the same scale, right? We took two different distributions. Let's say somebody took two different tests, and we took those distributions and we converted both of those into a standardized distribution using Z-scores. Well, now, whatever scores the people who took the assessments got on those particular on those particular tests, we can now convert those all into Z-scores and compare who's doing better or worse using the Z-scores because they're now all on the same scale of measurement. So Z-scores aren't the only standardized distributions. There are a lot of different standardized distributions. And those of you who have already taken my class in psychological measurements, we went over a couple of different kinds of them. We went over T-scores and staining scores and stat scores. All of those are different kinds of standardized distributions. But one very commonly understood one or used one is that of the SAT and that of the IQ. So SAT, right, I, I'm not sure if this is accurate now, because I know it did change a couple of years ago and then it changed back. But for an SAT, right, the population mean has been standardized to 100, and the population mean has been standardized to 500, and the standard deviation, did I say that wrong again? Sorry. So the population mean has been standardized to 500, and the standard deviation has been standardized to 100. Now, in an IQ test, the population mean has been standardized to 100, and the standard deviation has been standardized to 15. So that means we took a raw score, right? Everyone got raw scores on the SAT that they took, or the IQ test that they took, and we standardize it by converting their scores into z-scores based off a new mean of 500, and a new mean of 100, and a new mean of standard deviation, and another new mean of a new standard deviation. And I'm going to show you how we go about doing that. All right. Let's see. So the standardizing the distribution is going to have two steps. First, we're going to take the original raw score and turn them into z-scores, which we've been doing up till now. And then we're going to take those z-scores and transform them to new x values with the predetermined population mean and standard deviation. All right, so two steps. So let's look at that process, right? So a distribution of exam scores has a mean of 57 and a standard deviation of 14. The instructor would like to simplify the distribution by transforming all scores into a new standardized distribution of 50 and 10. So the population mean for the new standardized distribution is going to be 50, and the new standardized distribution has a standard deviation of 10. To demonstrate this process, we consider what happens to two specific students. We have Maria, who scored 64, and we have Joe, who scored a 43. So the first step is that we're going to take those raw scores and transform them into z-scores using the z-score formula, which is the raw score minus the population mean divided by the population standard deviation. So the raw score was 64. So 64 minus the mean of 57 divided by the standard deviation of 14 gives us a z-score of positive 0.5, right? So if we think about it, what does that mean? That means that the score of 64, right, is half a standard deviation above the mean, all right? So if we do that same kind of transformation for Joe had a score of 43. We just plug his score into the z-score formula. So 43, the raw score, minus the population mean of 57 divided by 14 gives us a z-score of -1. So we need to stop and think, what does a z-score of -1 mean, right? Because also you can check to see if you did the math right? First you need to understand that the raw score is less than the mean, right? So off the bat, if the raw score is less than the mean, you know that you're supposed to have a negative z-score. If you don't, you messed up somewhere. So you need to go back and retrace your steps. But this z-score of -1 means that a score of 43, right? Score of 43 represents in the standardized distribution represents a z-score of being one standard deviation below the mean, because it's a -1. All right. So step two. Step two is we're going to change those z-scores. We're going to take those z-scores, right? And we're going to change each z-score into an x value in the new. It's a very important part. The new standardized distribution that has a mean of 50 and a standard deviation of 10. All right. So Maria's z-score, right, is 0.5. That indicates that she is located above the mean by half a standard deviation. So in the new distribution, this location corresponds to x equals 55. All right. So you don't necessarily have to do the math in your head, right? What I suggest is that you put it into the X score formula that I discussed previously. So remember the X score formula is X equals the population mean plus the Z-score times the standard deviation, right? And so we just plug it in, right? So for Maria, her Z-score is positive 0.5. So the population mean that we're going to put in this is for the new standardized distribution. So the population mean is 50 plus the Z-score of 0.5 times the standard deviation, the new standard deviation of 10, right? So 0.5 times 10 is 5. 50 plus 5 gives us 55, all right? Try not to do calculations in your head when there's formulas available. It'll make the process a lot easier. Okay. All right, and so for Joe's score, right, is a z-score of -1, right? And that indicates that he's located below the mean by exactly 1 standard deviation. So in the new distribution, his location corresponds to x equals 40, below the mean by 10 points. But again, you don't have to do that in your head, because the questions that are in your homework or the questions that I give you on a quiz are going to be more complicated, where you're going to have to use the X formula. So let's do the X formula for this too. Let me get the numbers again. So it's 50 and 10, right? So X equals the population mean plus the Z-score times the standard deviation. So X equals, right, the population mean is 50 plus the Z-score of -1, right, times the population standard deviation of 10, right? So -1 times 10 equals -10. 50 minus 10 gives us 40. Gives us 40, all right? Okay. All right, so let's continue. And so over here, I tell you the steps, right? Converting to standard scores, right? So if we're going to convert to a standard score, you're first going to get your z-score, then you're going to plug your z-score into the conversion formula. You can do this for if it's for samples or for a population, right? And this is how to convert the standard scores back into raw scores. So you would get your z-score, plug z-score into conversion formula, right? And that's how you would do it in reverse. We're going to work on some problems with this. All right, so let's look at different standardized distributions and compare to population distribution. So In the original scores, right, the population mean was 57. If we standardize this into a z-score distribution, also called a standardized distribution, the mean would be 0. If we converted everything based off a standardized distribution that had a mean of 50 and a standard deviation of 10, well, the mean is now 50. The distribution hasn't changed. The distribution is the same, right? These are all equivalent. 57 in this distribution is equivalent to the 0 in the standardized distribution, which is equivalent to the standardized score in the new standardized distribution. Also, all of their accompanying numbers are equivalent in each of these different distributions. So score of 71 is equivalent to the z-score of +1 in a standardized distribution, and it's also equivalent to a 60 in this new standardized distribution. I'm trying to show you that these are equivalent. They're equivalent, right? Nothing's changed except the numbers, right? We just standardized them. Okay. So let's do some questions, right? So a population of scores has a mean of 73 and a standard deviation of 8. Mean of 73 and a standard deviation of 8. If the distribution is standardized to create a new distribution with a population mean of 100 and a standard deviation of 20, what are the new values for each of the following scores from the original distribution, right? So for this one, right, let's get you. All right, let us look at the worksheet that I created for y'all, right? And so in this one, the question is saying, hey, we're transforming a population of raw scores into a new standardized distribution. All right, so let's put in the information that we have, right? So from the population distribution, the population mean is 73. The standard deviation is 8. And the raw score, let's take 83. 83 was one of the raw scores, right? We're doing D right now, right? Oh, why did it change colors? Oh, okay, gotcha. So this is my first time using a stylus. So for this particular course, so it's all kind of new to me. Let's see. Okay. So then we would plug it into this z-score formula, right? So the z-score is going to be, oh, well, I don't have to use that. So z is going to equal, right, 83, which is the x score, right? Raw score minus the population mean of 73. And we're going to divide that by the standard deviation of 8. So 83 minus 73 is 10. 10 divided by 8 gives us what? Let's see. 10, what? 10 divided by 8 gives us 1.25. So the z-score is positive 1.25. So that means it is 1 standard deviation. The score of 83 is 1.25 standard deviations above the mean. Right? So if we put it into the new standardized distribution, right? The new standard distribution had a population mean of 100 and a standard deviation of 20, right? So if we put that in here and we plug it into this X formula using the new standardized distribution, population mean, and standard deviation, we're going to get X equals the population mean, which is 100, right? Plus the z-score of 1.25, right? Times 20, right? And that is going to give us, sorry, I'm going to use a calculator. Well, let's see. Give me 1 second, y'all. I'm having some technical issues. Right. So that's going to give us a, that's going to equal 125, right? So our new standardized score is 125, right? And so that's how you would transform the population of raw scores into a new standardized distribution. All right. And you would do that for all three of these questions. So I won't go through all three of them. So a population with a mean of 44 and a standard deviation of 6 is standardized to create a new distribution with a mean of 50 and a standard deviation of 10. We're going to skip A because A is the same kind of question as these. So we don't want to do that again, all right? But B is an interesting one. B is a reversal. B is one individual has a new standardized score. So this is the score on the new standardized distribution of 65. What was this person's score in the original distribution? Right? So in doing this problem, right, we're going to go sort of in reverse. We're gonna start by, again, this is the same steps, but we're using the different distributions mean and standard deviation. So in this one, x equals 65 is a score on the new standardized distribution. So to get a z-score, right, which is the first step, the z-score is going to equal the raw score minus the population mean, right, of the new standardized distribution divided by the standard deviation of the new standardized distribution. So z equals 65 minus the population mean of 50 divided by the standard deviation of 10. So that gives us 65 minus 50, which is 15, divided by 10, which should give us 1.5. But let me just make sure. So just as a reminder, I don't do these calculations in my head. I use a calculator. That's what it's there for. So yes, 1.5. So the z-score is 1.5, right? But now we have another step. So the second step is to take this z-score and plug it into the x-score formula. But now what we are using as the mean and the standard deviation in this x-score formula is the original distribution, meaning the population mean of 44 and the standard deviation of 6. So the raw score formula, right, is going to be the population mean plus the z-score times the standard deviation, right? So that equals x equals, right, 44 plus the z-score of 1.5 times the standard deviation of 6, right? And so adding all those up, right? 44, 1.5 times 6 plus 44 would give us 53. All right, let's just do the math for that. Just want to confirm, right? Let's see, clear. 1.5 times 6 equals 9. 9 plus 44 equals 53. All right. So that's how you would transform the scores if you were given information starting with the transformed standardized distribution and trying to convert it back into the original raw score distribution. All right. And so here are the answers for these questions, right? So a good cross-check that you should always do is make sure that before you take any of the quizzes, well, the exams, that you can do the learning checks, right? You can do all these learning checks without much difficulty. If you find yourself struggling, you can always come to my office or hit me up and we can discuss this, all right? We can go through some of these so that you'll have a better understanding of it. Okay. So some other questions. Let's go back to slideshow. So a score of 59 comes from a distribution with a population mean of 63 and a standard deviation of 8. This distribution is standardized to a new distribution with a mean of 50 and a standard deviation of 10. What is the new value of the original score? All right, so first step, change that raw score into a z-score, right? So that's going to be, the raw score is 59. So 59 minus the population mean of 63 divided by 8. So 59 minus 63 is -4. -4 over 8, right? I believe that's, let's see, -4 divided by 8 is -0.5. -0.5, right? So it's saying, hey, 59, right? Score 59 is below the mean by half of a standard deviation. Well, we can cross-check that, right? 63 minus 8, right, is 4 points. Is the halfway point between this and the first, and 1 standard deviation below the mean is 59. So we know that we did the calculation correct for the z-score, but we still have a second step, and that's taking that z-score and transforming it into what that would be in the new distribution with a mean of 50 and a standard deviation of 10. So to do that one, you again are going to plug it in to the x-score formula. So x is going to equal the population mean of 50 plus the z-score of negative, right? Let's erase that, of negative 0.5 times the standard deviation of 10, right? So negative, right? So negative 0.5 times 10 plus 50 is going to give us 45. Right, it's going to give us 45. So that would be your new score on the standardized distribution. All right, so looking ahead to inferential statistics. Remember, the inferential part is, hey, we're using a sample, and what we're trying to do is some kind of study so that we can get answers that we can generalize to the population that that sample came from. That's the whole purpose of inferential statistics. And so the interpretation of research results depends on determining if, a lot of times, if a treated sample, right, the sample that gets the treatment or the training program or the medication, is noticeably different from the population that it came from. So one technique for defining what is quote unquote noticeably different is to use z-scores. So this figure is conceptualizing a research study. So it's a diagram of a research study. The goal of the study is to evaluate the effect of a treatment. So what it's saying is that, hey, a sample is selected from the population and the treatment is administered to the sample. If after the treatment, the individuals in the treated sample are noticeably different from individuals in the original population, then we have evidence that the treatment does have an effect. All right, does have an effect. And so let's say our study is the distribution of weights of adult rats, right? Measured in, I guess, grams, I guess you could say. So here's a population of non-treated rats. So rats that have not been given any kind of treatment or medication or program or nothing. They're just the regular rats, right? The population mean of the regular rats is 400, right? And we have 2 rats, right? So distribution of weights for a population of adult rats, right? So the individuals, the rats that have z-scores near 0 are going to be typical or representative, right? So this score right here of 418, right? This is less than 1 standard deviation above the mean. So this is a very frequent weight for rats, right? Very frequent weight for rats, right? However, individuals with z-scores beyond the z-score of +2 and beyond a z-score of -2, we're going to say those are extreme scores. And we're going to consider those to be noticeably different from most of the others in the distribution, right? So if you get some kind of number that is higher than a weight of 440 or lower than a weight of 360, well, those correspond to a distribution, to a z-score of 2 standard deviations below the mean and even less, and 2 standard deviations above the mean and even more. All right, any scores that conform to those, we are going to say those are extreme scores and are noticeably different from most of the others in the distribution. Now, why are we saying that, right? Well, most, like I said, last class, most of the scores, remember, again, it's a population distribution with a relative frequency. So most of the scores, 70% of the scores are within 1 standard deviation above and below the mean, or 1 z-score above and below the mean. 95% of scores in a normal distribution, right, or a standardized distribution, are going to be between -2 and +2 z-scores, or 2 standard deviations above or below the mean. So 95% of your scores in any normal distribution are going to conform to those rules of thumb. We're saying that, hey, we got a score that is far and above outside of 2 standard deviations, either above or below the mean. So that's a really extreme score, and it doesn't happen very frequently. Remember, we talked about the tails, right? These are tails, but the tails are denoting frequency. So scores that are 2 standard deviations above or below the mean, they happen less frequently than scores that are closer to the mean. And so they are very different from the scores that we would expect. And if we get something like that, we're going to say, well, they are extreme and noticeably different from most of the other scores in the distribution. All right. So last week, Andy had exams in chemistry and in Spanish. On the chemistry exam, the mean was 30 and the standard deviation was 5. And Andy had a score of x equals 45. On the Spanish exam, the mean was 60 and the standard deviation was 6. And Andy had a score of 65. For which class should Andy expect a better grade? Now, I'm not going to work through this problem, but I'm going to tell you how you go about doing it. Right? You should know this already, right, from this class. First, you're going to transform these two into z-scores. So you're going to get a z-score for the chemistry test, raw score, and a z-score for the Spanish test, raw score. All right. And then once you have a z-score, right, you are going to compare the z-score and see which one is greater or lesser. The one that's greater, well, the person Andy should expect a better grade on. And in this case, if we do the z-scores, right, it's going to be chemistry. Chemistry is where he's going to expect to have the better grade. Okay. So question, true or false? Transforming an entire distribution of scores into z-scores will not change the shape of the distribution. All right, that is true. Each score location relative to all of the scores is going to be unchanged. So the shape of the distribution is also unchanged. True or false? If a sample of 10 scores is transformed into z-scores, there will be 5 positive z-scores and 5 negative z-scores. All right, that will be false. The number of z-scores above and below the mean will be exactly the same as the number of original scores that are above and below the mean. So here are the answers to that one. And that brings us to the end of this particular chapter. All right. I want to thank you for sticking around with me. Again, like I said a little bit earlier, if you have any questions, you could hit me up after class. If this is a regular class, if it's an online class, you can, or if it's not, or if it's a regular class, either way, you can contact me through Canvas. All right. And or through my email, right?